record the session so everyone can see it later, can watch it later. Okay, first let us work a little bit with the theory. Maybe it would be better to remember some things from the very basics of system engineering and automatic control from your bachelor degree. So here I'm going to talk about the block diagrams. As you may know, we have different ways to present a system. One of them is block diagrams. The other one is a state space. One of the other ones is the equations, the differential equations, and the different methods to show the system. But one of the important ones is block diagrams. And what I mean with the block diagram is that let's say we have a plant here that receives a signal and produces an output, which is called Y. And then we want to control this. So we add a controller block here and we connect it here to the input of the system. And after that, we have the U here. And before that, we have a closed loop here, which is our reference. Here plus, here minus, here is the E, here's the error. And then we get it here. And we assume that here our sensor doesn't have any dynamics. So that is actually the most easiest and simplest method that we can show the system. But in the real world, it isn't like that. What in real world happens, which is the difference in this course, is that here we have some sort of noise, which we show with a W, which is actually our noise of process. Noise of process. And after that, we have another noise here. So let me cut these and move them here. So we have more place here. And after that, we have another error, which is actually our measurement error, which we show it with V, and we name it measurement error. And after that, what we have is the Y. That means we are not able to actually measure what's here, but we can actually measure what's here. I mean, after the noise is applied. That is the difference between this course that we are doing right now, I mean, Sensoren für Fortgeschrittene, and the one that you had in your bachelor. So let's talk about this Y. So as you may know, in this system, in this part, in this plant, in this G, we have different kinds of internal states, which is like X. But what we can measure is actually not the X, but the Y. So the question is, if we can in a way get this Y and analyze it or process it in a way so we can have an estimation of X. So imagine that this system is actually a car, and here we have the vibration. X is our vibration, and Y is the temperature of the motor. So imagine that we can actually measure the temperature of the motor, but we cannot measure directly the vibration. That means that we have two states that we would like to have, but we can only measure one of them. It would be really great if we could measure one of them and estimate the other one using this. That's what is called sensor fusion that we want to do in this case. So let's duplicate this slide and talk about Kalman filter. What Kalman filter does, so I already explained how what is the objective of the thing that we want to do here. We want to have the output and we want to estimate the input that we cannot reach. We want to estimate it. How we can estimate it, one of the ways, and the best way till now, maybe you guys can invent another one, but the very best method that we have already there is the Kalman filter. And no one could ever done a better job than Kalman as an observer. What we are trying to do is called observation. So let's say we have, let's delete this here, make it easier. Yeah, so what we are trying to do is estimate this X that we cannot reach using Y and U. We can get both of them here, use a block, which is not a filter, which is an observer, but it is called Kalman filter. What Kalman filter does is actually estimating another state, which is called X hat. And we try to minimize the distance between X hat and X. And after that, we can say, okay, X hat is X. But we don't have directly access to this X. So how can we assure that this X hat converges to X? That's why we have another another feedback here from y. So we will also produce, other than x hat, we will also produce a y hat. And then if we try to reduce, to minimize the difference between y and y hat, so we can assure that y hat is converging to y, and we can assure that x hat is converging to x. That's actually the idea behind this. But what happens inside of this magic block, which is called Kalman filter? Let's take another look. So what happens in Kalman filter is actually this. Let's bring the whole thing here. What is happening in Kalman filter is actually something like this. So we get here u and y, and after that, we bring it here, plus and minus. And after that, this y will come here, and here we have a gain, which is Kalman filter gain, which I will explain later what that is. Oh, sorry, I drew it wrong. Yep. Yeah, sorry. So it will come actually here, and then it goes here. Okay, to the k, which is Kalman filter gain, and after that goes here, and then we have this u, which goes in here, and then the whole thing goes to the plant again. And then here will y hat be produced, and then from y hat we have this. So as you can see here, in this block, this is our Kalman filter. So, as I told you before, we don't have direct access to this x. What we can do instead, we can actually simulate the whole system again. So as you can see here, we had our plant G here, and we have the same plant here. And we have the same plant here. What we are doing here is actually simulating the whole system, the whole real system again, so we can access x virtually. That means that the idea behind Kalman filter to estimate one of the internal states of the system is actually that we must have the model of the system. If we don't have this G, we cannot use Kalman filter in a right way. That is what is happening behind the Kalman filter inside this magic box. Inside this magic box. So about this Kalman filter gain, there are different methods to calculate them. There are some theoretical methods, there are some algorithmical methods, and there are some already implemented functions in MATLAB for that. So the cool thing about MATLAB is you can define this G in any method that you want, whether transfer functions or block diagrams or a status space representation and so on. And then you have a built-in function that you can call, and then you can say, okay, design a Kalman filter for me, and then the result of this will be this gain, this Kalman filter gain, that helps you to estimate this internal state. And then here is x hat. Don't forget to say it. Yeah, exactly as I told you before. Then you can estimate this x hat. Okay, so till here we talked about block diagrams, and we explained everything in a control point of view. But from now on, we are going to look at it in an algorithmic point of view. What happens in an algorithm? Yeah, you can understand what is happening behind the Kalman filter, but how can we implement it in an algorithmic way so we can use it in our code? So the method that we can use it as an algorithm. So let's draw this block diagram again. So here's G, here's our noise of process, here is our noise of measurement, here's our input signal, here is the X that we want to reach, and here is the Y. And we have this U and we have this Y. And we have two major steps here, which I am going to just copy and paste. It will be really easier. Yeah, exactly. So we have this measurement update. And then we have the time update, which I'm going to explain right now. Okay, so okay. and here is our x hat. So if you want to do the Kalman filter in an algorithmic way, we have this block that we can implement in our code in an algorithmic way, and we can get the estimation of the internal state that we wanted to measure. So I'm not going to go deep into these steps. You know them already. They are a little bit complicated. Maybe you know them already from this course. I'm pretty sure that Benjamin told you already. And if you had the course Control Theory or Regelungstechnik with Professor Zufker, he explained it perfectly. So I'm not going to repeat it because I'm not that qualified to explain such thing. But as I told you before, and another really important point, that we have here our initial condition as well. And here we have covariance matrix R, and here we have covariance matrix Q. And this covariance matrix, yeah, let's explain it later. So after we are done with algorithm, I will go a little bit with state space. So state space is one of the ways that you can present the system, the dynamic system, with like you can present a set of differential equations in an algebraic form, and they have normally this standard form of x is equal ax plus bu, and y is equal, no, sorry, x dot is ax plus bu, and then y is equal cx plus du, which this d is normally set, is usually 0. And yeah, this is a state space, if you may remember. And why is this x and y capital? Because they are vectors. And this as well, and this as well, and this as well, and this as well. So they are vectors or matrices for MIMO systems. So what that means is that actually this x can be containing more states of the systems. That means, let's say we have a two-dimensional system. This x is containing x dot, y, and y dot, which is actually our case in this practical. Exactly. And this is called a state vector. But this, what you see here, what I wrote here, is in continuous time. If you can do the same, in discrete time, these set of equations will change in this way. So let's say we have x in the moment of k is equal to a, which is different from this a that we had in continuous system. They are not the same. X k minus 1 in the previous moment plus b u k minus 1 and y in the moment of k will be a x, oh sorry, c, oh let us change the name to h x k1 k minus 1 plus this part is 0, but I'm going to write the 0 so we don't forget u k minus 1 in previous moment, and after that we will add the other two errors that we had. One of them was w k minus 1, which was our process noise, if you remember, which is actually wrong because we have another g here, but in this case we will assume that the whole thing would come here. And here we have vk. Why not k minus 1? Because we are measuring in real time. So here we don't need, here is the noise of measurement. We don't need to do a minus 1 because we are measuring right now at the moment of k. And this one will be called measurement noise. Okay, let's assume that these two noises are white noises, and that means that they have a normal distribution with a mu of 0 and the covariance of q, and this one has the normal distribution again with the mu of 0 and the covariance matrix of R. And yep, that's all you need to know about theory for Kalman filter. But last but not least, let's talk about the Cardon transformation as well. formation. So as you may know, a car has different degrees of freedom. So let's say here's our car, which is pretty nice, Mercedes S-Class. And then here is also, from this point of view, as you may know, we have also different angles of the car, which are called phi, psi, and theta. And then we have x, y, and z, which if you have this x, y, and z, and you want to get, sorry, if you want to get this phi, psi, and theta, you will need this Cardan transformation. And for those of you that you already had this course, vehicle dynamics with Professor Tobias Brookman, you already know that there is a matrix form for that as well, which has the different angles here. So this is already implemented in the files that you got, but I just wanted to tell you what Cardan transformation is, so we can have a relationship between those degrees of freedom of a car. So the other thing that I wanted to mention before we begin hands-on with MATLAB programming was the sensor fusion. Sensor fusion. So as you all know, there is a sensor in some cars which is called GPS, and your phones have already been there. The thing with GPS is that GPS signals are not available in any position. I mean sometimes if you go somewhere between mountains and you don't get any signals, your angle with the satellite is somewhere really bad, or you get into a tunnel or something like that. So you won't get any signal from GPS. So how can we compensate for that? So let's say we drove into a tunnel which we don't have any signals here. But theoretically, if we know our position here, and we can fuse this sensor of ours, this GPS, with an IMU, with the accelerometer. Theoretically, if we don't have any noise, we can measure, okay, here, okay, here, okay, here, how the path of the car is changing, and we can actually compensate this. So if we have an accelerometer in two directions, in two axes, we can do an integration on it, and then we can get the velocity, and then we can do another integration, and we can get the distance, and then theoretically, we can have an estimation here where we are, even though we don't have any signal from GPS. So in this case, in this example, we are actually trying to combine and make a hybrid sensor from those two, one time GPS and one time IMU. So the thing with GPS, so let's say here's the x-axis, and GPS says that we are somewhere here. So as I told you before, every sensor has a noise, and noise is everywhere. We cannot completely make it away. So here is the place that our GPS suggests that we are. So yes, you may say that we are most probably here, but it doesn't deny that we can be here. We can be here, but the thing is, the possibility of us being here is less than here. But nevertheless, we could be here. The thing is that because of the noise, we have a normal distribution here, and we don't have a really sharp signal here. The same thing with IMU. The same thing with IMU. So this one is GPS, and the same thing is with IMU. So IMU says that we are someplace here in the middle. But it doesn't guarantee that we are exactly here. We could be here. We could be here. We also could be here. So it doesn't guarantee. What we can do is combining these two and and fuse these two signals using signal fusion, and then we can say, okay. So if we use both of these sensors, we will probably land somewhere here, which is which is not as wide as GPS. So as you can see here, this curve is pretty wide, and this curve, this IMU curve, this IMU possibility of position is not that exact. It's not that accurate. So this one is not reliable, but it's fast, and this GPS is reliable. And if we combine both of them together, we can end up with this curve, which is fast and reliable. That's what we are trying to do in this practical. So let's finish with the theory and get to work with MATLAB. So I already prepared a set of data. So let's click on edit and get to the editor environment of MATLAB. We will start with CLC, clear, and close all. The CLC clears our command window, clears every variable in our workspace, and close all closes every last window, charts, diagrams, and so on that we had opened from last code. Let's save this as app2. So we have CLC clear close all. After that, let's load a set of data that I already prepared with parentheses, of course. And this is called Kalman data.net. And after that, we will do dt dt of GPS is equal to, let's say, 0.6, exactly what you had in your practical. And after that, we will define the system matrix A of 1 dt GPS and the other line 0, 1, and close the bracket. Oh, I didn't open the bracket at all. Okay, so here's our system matrix A. Let's check. Why isn't it opening? Yes, exactly. So let's define also the output matrix, the command window, the command matrix B, which is zeros 2 by 2, and then we have U, which is zeros 2 by 1. As I told you before here, these x's and u's are actually vectors. These x and u are vectors, and these a and b are matrices, as we saw here. So why 0? Because I'm just initializing and nothing else. We will change them later. So after that, what we want to do is defining the R, the covariance matrix of R, which will be. So first, let's go to this data real or data measurement. Let's go to data measurement. So as you can see here, the data that I called here is containing 3 variables. Is in a 1-by-1 structure, which has 3 fields. One of them is time GPS, which is just a linear vector, nothing much. After that, we have the X. Actually, we have 3 sets of these. One of them is the measurement, one of them is the reference, and one of them is the real. And we are using just the measurement and real. So we assume that we don't know the real. We are just going to plot it so we can compare our estimation with the real data. But nevertheless, as you can see here, we have our measurement of X, and we have also the data from IMU sensor. As you can see here, here's our acceleration in x-axis. So just wanted to mention. And what we want to do right now is defining the covariance matrix of R, which is actually diag of, let's define it in this way. So 4.6 times std of data measured dot. If I click on dot, I can access the fields of the structure, and then x, and then in power of 2. No, I actually have to use measure ref. Yeah, exactly. So, and in power of 2, and the same thing again. So if I click on run, you will see what this diag does. What this diag does is actually getting 2 variables which are the same in this case are the same, and make them and put them on the main diagonal of the matrix, and the rest is 0. So here we have a 2 by 2 R covariance matrix, and after that we have the same for Q. Oh, not the same, but diag of 0 and 50, but the result would be similar with R. And after that, we have the matrix H, as we explained before. This matrix H, the output matrix H, will be 1, 0, 0, 0. Why 1, 0, 0? Why 1, 0, 0, 0? Because we only want to check here the X, and we don't want X dots or anything else. So that's why we are defining our Y in such way with this H, because we only want this one and nothing else. That's why. So let's do the initial conditions. So I am going to define my x hat, but I'm not going to name it x hat. I'm just going to name it x small. So x hat or x small in this case will be, we want to initialize it. So for initialization, we will just use the very first sample that we read from x, and that would be data measure dot x. Which one? The very first one. And that was our That was our initialization for the position, and the initialization for the speed, for the velocity, will be 0. So we initialized our position, and then I'm going to define the p as well. So p will be 0's 2 by 2. P is actually this here. Let me change this. So here is p, which is usually 0 because we don't have exact transfer of u and the output. So let's get back here to p. After p, we want to initialize our parameters, which are dt of our IMU will be, let's say, okay. And after that, let's get back again to the theory. As I told you before, what we are trying to minimize is the MSE of this difference. So I have to define this part as well and try to minimize it, do a summation on it and try to minimize it if possible. So I'm going to define MSE of P measurement is equal to 0. The same thing with P estimation and velocity measurement and velocity estimation. Okay, so why is that? Because, as I told you already, where was it? Yeah, exactly. So you can see, no, wait a second. Yep, as you can see, this x is not only the x, it's actually a matrix of states which has x, x dot, y, and y dot inside of it. The same thing is with x hat. This x hat is 4 by 1. Then in this case that we are going to solve is 2 by 1, but nevertheless, it is not only a scalar, it is containing the x hat, the x dot hat, the y hat, and y dot hat. Let's get back to MATLAB, if Microsoft allows us. Okay, perfect. So let's start with the Kalman filter. For the Kalman filter, we need a 4. Why? Because the whole thing is recursive. As you can see here, the whole thing is recursive. So I'm going to use 4. So let's say I for 1, 2. Let's use j for now. 1, 2. DAT of GPS divided by DAT of IMU. So here we are trying to k is equal. Let's define another counter here. So I minus, actually that is. Am I forgetting something here? Wait a second. Let me think. No, actually I have to do another 4 first. For I is equal to 1 to the end of the length of the matrix, all of the measurements that we already have. And let's start it from the second one, because the first one is the initialized one that we already have. So let's say length from 2 to the length of data measurement ref, or just measure, and that's x. And after that, let's define our u, which is 2 zeros in a row. And after that, let's use another 4, which is j equal to. So actually, this one is for the recursive Kalman filter, and the second one is for fusion of two sensors. You will see soon what that means. So we will say j is equal to 1 till dt of GPS divided by dt of IMU. Let's write the 2 n's here so we don't get the error. And here I'm going to define the k, which is I minus 1 multiplied by dt of GPS divided by dt of IMU plus j. And then let's round the whole thing. So round the whole thing. So after that, what we want to do is preparing for sensor fusion. Here we will define another variable which is called AV. This AV will be actually our measured data, but this time the acceleration of x. So it will be data measure. Let me think. Data measure dot. What was the field here? Data measure AXV. Yeah, exactly. Okay. So AXV, which index? The K index. And yep, that was it for the sensor fusion. And now let's do the Kalman filter. For the Kalman filter, first, let's get back again to the theory. As I told you before, what we are trying to do here is actually simulating the whole system all over again. Why? Because we already have the model of the system. And we have our K now. No, we don't have our K, sorry, yet. But what we are trying to do is to simulate the whole system again. That's actually what we are going to do with x hat. This, as you can see here. So as I told you before, I'm just using this x here, but it's the x hat, the same x hat that I already explained. So here our x hat will be a times x plus b times u. Sorry, u. Yeah, exactly. So you may ask, okay, we had x dot is equal to a multiplied by x plus b multiplied by u. Why is it like that? We had our x k minus 1 and we had here xk. Why is it like that? Because we are programming. And if we are programming, we don't need them anymore because we are just going to do it step by step. So the x that you are seeing here is only the estimated value of that only moment. That means, as you can see here in data measurement, for example, for x, we have so many data. But here, for the Kalman filter, for this line, we are going to estimate just this moment, just x of k. So what you are seeing here, this x is actually the x of k, x in the moment of k, and this x is the x in the moment of k minus 1, and this u as well, in the moment of k minus 1. So what you're seeing here is actually not going to be a vector. Yeah, it's going to be a 2 by 1, but it's not going to be 1,000 by 1. The 2 by 1 is because one of them is the position and the other one is the velocity. And this is not going to be a long vector because we are just doing one single step of Kalman filter in this per line, per eye. So don't forget what we are going to get from this x. This is actually x of k, and this is x in the moment of k minus 1. So after that, we are going to write our p. So what I'm trying to do from now on is only implementing these 5 magic formulas that does the whole thing for us, and we just have to follow them blindly. Chat. K is not the Kalman gain. K is not already the Kalman gain. K is actually the a counter that connects this I and J together. I mean, like, okay, let me explain it here. Good question. This K is not the Kalman gain. So, as you saw, we have a dt of GPS, which is 0.6. And here we have a dt of IMU. The sampling time of our IMU is this. So if we want to fuse these two sensors, if we want to combine them together, how can we do that if this measurement is getting updated every 0.6 seconds and this one is updating every 0.03 seconds? So we need another counter that we can fuse this. So we will get this sample first, and then we will get, I don't know, maybe like, yeah, 20 samples, sorry, 20 samples of this, and then we will get 21st sample here. So K is actually just a counter that is helping us to sync these two timings together, nothing else. This K is not the Kalman K. Good question. So what happens if I close the chat? Can I access it again? Yes. Okay, nice. So here the P, as I told you before, I'm just blindly implementing every formula that we have. So A times P times A transposed plus Q, and the next step is K of K. So this K, this capital K, is actually the Kalman filter. This capital K. This K of K is going to be P times H transpose times parentheses in the parentheses h times p times h transpose, of course, because why not? Yeah, plus r is pretty, and the whole thing would be, must be inverted, but since the inv command is no longer supported from MATLAB, we are just going to use power of -1. So for the next step, what we have is update estimation with the measurement, and that would be z of k. That is actually the y that I told you before. So this z, where was it? Yeah, exactly. This, so in the course, in this practical, here is called y, and this is called z. So don't forget. So I know maybe it's one of your questions that what is z right now? So the z is actually here. This one is z, and this one is y. But because I don't want it to explain it in a hard way, I just use y. So that's why. So let's get back to MATLAB. So z of k, and this is actually, sorry, this is not y, this is y hat of the moment k, which will be, or is it? No, it is actually k, because we are going to use data dot measure, no, sorry, data underline measurement, data dot measurement, that's x, data underline measurement x on the moment of I. So we updated our estimation with our measurement, and the last step is updating the error covariance, and that would be p is equal to, so we want something like this, 1001, but there is a really funny function for that, which is called I. So we write I2, and as you can see here, if I write I2, the result will be exactly the same thing that I wanted. It's actually I2, but since I is too general, they use this function I. So I of 2 minus k of k times h, the whole thing multiplied by the previous p. Let me check everything very quickly. Yep, it's okay. So now that we calculated everything and all of the 5 steps of our Kalman filter, as we showed here, 3 of those were measurement update and 2 of those were time update, but actually time update happens first, the predict happens first, and the correction happens after that. So the first 2 things that you are seeing is actually these 2 things, which are predict. Let me write that down here. Predict, and here is correction. So what we are going to do right now is eventually trying to reduce this MSE as much as possible. So neoscale error. So defining it would be too much of time consumption. So I'm just going to copy them and paste them here because I already done them. So as you can see here, every time in every step, we have the same thing plus another thing because it's a summation. And after that, we have this calculation here for these 4 MSEs that we already defined, and that's why we initialize them here. Now we are adding them up together, so we can minimize them, we can monitor them, and see our performance. After that, what we want to do is actually save this x, and why? Because as I told you before, this x is just x of k, of just one moment and nothing more, of just one moment and nothing more. That's why we have to save it in a vector that we can use it later. So what I'm going to do is defining another x hat vector, which this x hat vector, the ith index of it will be this x, the first one. Let me explain it again, so it is clear. So let's say our x, our actual x, and our x hat, sorry, or was it right? Yep. Let's say we have the state vector, which is containing here x and here x dot. Okay, so this column and this column, there are 2 columns. There are 2 columns, and let's say we have 1,500 measurements. So they are going to be 1,500 measurements. But for calculation of x hat, which is equal to x hat and x dot hat, we are not going to calculate them at once. Why? Because this process of Kalman filter is actually recursive. So we just have to do it one by one. For how many times? For 1,500 times. That's why we have our 4. So the first 4, why can't I write anymore? Ah, come on. Okay, the first 4 is for this, and the second 4 is for this. So the first 4 is going to be run for 1,500 times, and we are not going to calculate the whole x hat at once. What we are going to calculate is only the x hat k and x dot hat k. And this is what Kalman filter gives us. After that, we can get all of these. Let's name it sorry. In this step, in ith step, and in ith step. After that, we are going to augment them all together and get this x hat. But the very important thing to understand is that Kalman filter doesn't give us the vector of x hat directly. Kalman filter is a recursive method that is going to give us the state of just one point of time, which is I. Just one point of time, and the task of augmenting them all together, putting all 1,500 lines together is our job. So here is x hat 1, x dot hat 1, after that x hat 2, x dot hat 2, until x 1,500 hat and x dot hat 1,500. So Kalman does not do this. We have to do it ourselves. So I'm going to write here manually. That's what we are doing here in this code. So that's what you are saying. So I told the code, okay, I have a vector, x vector, I want to define it, and I want to assign my x, my position, my first one. So this is x1, and this is x2. So assign x1 to this, to the first one, and assign this one to the second column. That's what we are doing. So here's the x vec. I is equal to x1, and after that we have v of x, sorry, the ith element is equal to x2. Okay. And after that, do we need the... No, we don't need the other ones. Okay. Let's run this code till here and see what happens. So as you can see here, this x contains only 2 variables. This one is my speed at the very last moment of the I is equal to 2,517, and this one is my position there. So as you can see here, this x, which is the result of the Kalman filter, is only for one point of time. And the vector that I saved here, these 2 vectors, are vx, yeah, where's the other one? X vector, yeah, exactly, here. So as you can see here, this is the vector that I saved but why is it like that? Why are all of them just like each other? Okay. It seems that I have done something wrong. Run again. Why? Is the same thing happen with phi of x? Yeah, it's 0. Pretty funny. I don't understand why. What am I doing wrong? Let me check again. Our Kalman filter doesn't work, apparently. Okay, this one is correct. This one is also correct. This one seems to be correct too. This one too. Ah, yes, exactly, because I forgot one of the steps, and that was the calculation of x hat. Okay, sorry. Okay, so the calculation of x is the further state plus the correction, which is done in this. Okay, so now our Kalman filter should work. Yes, here is the very last state, and here is our x hat vector that we manually augmented together. And that is the same thing, but not for the position x, but for the velocity x dot. So I'm going to write here x hat vector, and this one is actually x hat, and this one is x dot hat vector. And here is single step k, and here is the vector. So here we have scalar and here we have vector. Okay, so the only thing that we have to do is plotting the result and see if we already did come up with the task. So once again, let's get back here. So as you may remember, we said that we have an internal state of x that we cannot reach, we cannot directly measure. But since we can measure x, and since we have the whole system model, we can simulate the whole system once again in our Kalman filter, and using a Kalman gain, which we got from a few complex mathematical relationships, we can get an x hat, and since we are trying to minimize this difference between y hat and an actual y, so we can prove that x hat will also converge to x. Again, we cannot directly measure one of the internal states of this plant, which is x, but we can estimate it using a Kalman filter, which the result would be x hat. So what we are trying to do now is plotting this real x and plotting this real x, this estimated x hat, and compare them together to see how the performance of our Kalman filter was. But nevertheless, you may not forget that in real world, we cannot access this and print and plot a beautiful diagram and say, hey, look how beautiful x hat is following x. No, we cannot do it in the real world. We are doing it here just to compare, just for the comparison to see if really x hat is converging to x. So if we had directly access to x and we could plot it, it would be really idiotic to calculate x hat. So in this case, that we are going to compare these two together. Now we are going to compare these two together. You may not forget that we don't have access to this. We are cheating actually right now. We are going to just monitor if our Kalman filter good works. That would be all. So we don't, in real world, we don't have direct access to X. But here, just to show, just for seeing. So what I'm going to do is opening a figure. I'm going to open a figure. After that, I'm going to use a subplot. My subplot will have two rows, one column. The second part would be the position first. So I'm going to write plot. What we are going to plot first, x-axis. First x-axis. Our x-axis will be. Hey, wait a second. ax1. Wait, what is ax1? Mm. Mm-hmm. 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 Okay. Okay. But first, before we do so, let's define the time vector, which will be from 0 to dt GPS till t end. What is my t end? Wait a sec. Okay, let's first define t end is equal to data dot measure dot time GPS, and the very last one, yes, and then a vector from here to here. But I think that would be better. Now let's start with 0, see what happens. Maybe it works. Okay, so we are going to plot our x-axis, which is our time vector, and in the y-axis, we want to print this. Let's see how it works. Yes, as I thought. Okay, t is 2518, and this x-vec, where is x-vec? Yeah, exactly. So let's start from the first one. Exactly, okay. We got the first plot. So let's hold on so we can plot two things on the same subplot. So let's say again plot, but this time t. Actually, you know what? Let's bring this here, and we can data underline first real, then x, then hold on, then plot again t data estimation. No, what do we have? Measure, sorry. Measure dot, did we have measure? Dot x, yeah. Okay, okay, let's turn on the legend. Okay, first x label is time, the y label is position x. Then let's turn on legend and write for the first one real. For the second one, the very first data set that we plotted, that very first curve that we plotted is the real data. The second thing that we plotted is the measured data. And the third thing that we plotted is our x hat vector, which is the estimated data. So I'm just going to write here estimated. Now, if we click on run, we can see that we have our legends here. Rio is the blue one. Orange is the measured one that our sensor read, and the yellow one is the estimated one. Let's zoom a little bit in. As you can see here, this blue curve is actually the real position of our car. The orange curve is what our sensors measured, and this yellow one is what we followed, which is actually not optimal. It is better. It is better than the measured one. It has less noise than the measured one, the orange one, but it is not optimal. And that is actually one of the parts of the task that you have to try to make the Kalman filter, the estimated state via Kalman filter, which will be more robust to such noises of the measured signal. But as you can see here, we could actually follow this, and you may not forget that we didn't have access to this x directly, and we completely blindly estimated the whole thing. So actually, the you may say, okay, we can see the blue one. Okay, we can see the blue one, but imagine that this blue one is the real one, and we didn't have access to it, and we could somehow, using Kalman filter, estimate it. So in real world, you won't have a blue one here, a blue curve here. Yes, okay. So let's do the second subplot as well and close this session after all. So I'm just going to copy the whole thing here. Another plot, this time the second subplot, and this time data real.x. It won't be data real.x, but this time we want to do the same thing with velocity. So what we are going to do is, yeah, changing this. And from the measurement, hey, wait a second, don't I have the measurement? Real will be b of x. Okay, currently I don't have the measurement. I don't know why. It's okay. Real and estimated will be enough for us. Oh, I did something wrong. And that was copying this figure here. And this is velocity. And this is v of x. And now click on run. Exactly. So as you can see here in the first subplot, we have our position in the time, and in this one, in the second subplot, we have v of x, the velocity of axis x throughout the time. But as you can see here, our estimation is not that good. It is pretty noisy, and that would be the task of the next week, to try to reduce this noise and try to have a better estimation and more robust estimation of the whole state. So yeah. How can you then estimate without measuring? Yeah, you're right. But yeah, we have to have a measurement to estimate. But I forgot it. I forgot to index it here anywhere. So yeah, you're right. We have to find it. I just wanted to save time. That's why I didn't do it. But let's go to the measurement and see where exactly it is. I think that. Wait a second. Yeah, I calculated it somewhere here. That's why I could do the estimation. Where did I do the estimation? At x here. I did the estimation, but somehow I can't find it anymore where I saved it. That's why. Let me check in my source code. Is it an AXX? No, that's actually acceleration. That's not the speed. Mm, wait a sec. Interior.ax. Absolute measure. Yes, 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 yes. I forgot to calculate this. I forgot to calculate this. Okay, yep, okay. So just a sec. After Vx, exactly here, what I forgot is V um, measure of I. So the thing is, our IMU, as you can see here in data measurement, in this set of data, in this structure, if I open it, I have only time vector, I have x, the position, and I have a of x. And I don't have any speed, any velocity. I just have the position and the acceleration. So what I have to do is manually differentiating between these. So I'm just going to add another vector here, and I'm going to write here a square root of data, data measure dot data measure dot x, right? Yeah, of x of the ith moment minus uh, the same thing in the previous moment, and of course the whole thing in parentheses divided by dt GPS. That should work. Okay, that doesn't work. Wait a second, wait a second. What am I doing wrong? Okay, the whole thing. Yeah, because we have minuses, right? Wait a sec. dt GPS. Yes. And then before these, I have to add an apps here. Is it right now correct? Or no, I have to add apps here. Okay, it has to work right now till line 73. Yeah, of course, because I didn't write it down here. Um, yeah, and measured and estimated. Wow, our estimation is really nice. As you can see here, or am I doing wrong? Wait a second. Yeah, the second one is the measured one, and this one, exactly, exactly. But it shouldn't be like that. It's a little bit, I don't know. So as you can see here, we have again our real data, which is blue, our measured data, which is orange, and our estimated state, which is yellow. It's not that optimal, but as you can see, it is really better than the measured one. The measured one is absolutely clutch, but I think you can work on this code, so you can reduce a little bit um, of this jumpings of the measured estimation of the estimated state using Kalman filter to do it better. And yep, that was all. I just wanted to show you how to code it and understand a little bit of the theory, the application in another language, in another method, so maybe you can understand it better. So it is velocity somehow estimated based off the position, because measured velocity differs a lot. Yeah, I don't know what happened here. It should be actually right. It should be actually right, since as you can see here, the measured position and the real position are not that far away. So the measured velocity may not be like that. I don't know what this is happened, but I will correct it and put the corrected version online. So I will upload it online so you can check it, and I will tell you in the forum. But it has been already 19 minutes, so we have to close this session. But yeah, as I told you, I will find the problem, because I coded everything here completely live. So maybe I did something wrong. I don't know. I have to check it. But yeah, as I was saying, You're welcome. Sorry that I couldn't, that I wasn't that ready to answer you right now, but I will. But I will answer you. So as I was saying, I just wanted to show you the idea behind the Kalman filter, the application in real life, and using just one sensor to estimate other states of the system that we don't have directly access to. And we saw a practical example here as well. So of course, this was just in one direction. Your practical will be in many directions. I mean, like X, Y, Z, phi, psi, and theta. It's going to be much complexer for you guys, but just an example. I wanted to show you how it works and what is the reason behind that. And maybe it helps you. I hope it helps you to hear the whole thing from another perspective, another from a view, because I know the professors in the university just focus on the theory and don't show you the practical application. And I would be really glad to show you how to. So that'll be all for this session. Thank you for your participation. Unfortunately, we don't have any time left for answers and questions, but I think that's not the case. We will have the next session next Friday. I hope you can start with the practicals. So summarize all your problems and you can ask them next week. Again, thank you for your participation. This video and the code will be also uploaded to Moodle. And yeah, till next week. Take care. I have actually some questions. Can I post them in the forum? You may stay and ask your question. Okay. If someone has question, he or she may be here and ask. If someone wants to leave, you're free to go. Okay, you may turn on your mic and speak if you want to.
How like at the very beginning of your code, how did you make the A matrix?
The A matrix. The A matrix is actually. Let me demonstrate here. So here is x, and here x dot is equal to ax plus bu, but this one is in the continuous form, in discrete form. As I told you already, we have xk is equal to xk minus 1 plus bu. So now your question is, why is a like this? A is equal to 1 dt GPS, and again 1 here and 0. That is now your question. So let's say, what is the relationship between so first of all, the very important thing that you have to understand is what are these columns and what are these rows for. So this is actually a question of automatic of control and system engineering. But okay, we are going to answer it. So we said a times b, a times x. So what is x? What is x? X is going to be x and x dot. Don't forget that this is actually a vector of two states, not only one scalar state. So, and let's say this is x k and x dot k is equal to x k minus 1 and x dot k minus 1. Is that right? So as you can see here, this is xk and this is a, and this is xk minus 1. That was what we had in this grid form, right? Do you agree?
Yes.
Okay, so let's do the multiplication and see why is it in this form. So if we expand this this matrix multiplication, it will give us xk is equal to xk. So this will be this multiplied by this, right? Xk minus 1 plus x dot k minus 1 times dt of GPS. Right?
Yeah, so actually for our...
That's actually differentiating. That's actually differentiating in this grid form. You see? Isn't that familiar? Isn't that familiar? Let's bring this to the other side. Xk.
Yeah, I understood it. But if we have two dimensions, then our A matrix is like 4 by 4, right?
Exactly. Minus 1
okay.
dt GPS, and this will be x dot k minus 1. That's actually this. So we change it to this, and we changed it to this.
And we don't have any constant velocity because I saw that we have acceleration, right?
And no, we don't have any constant velocity. No, the velocity is changing actually.
Okay.
Yes.
Okay.
Yes.
That was it. Thank you.
Okay, you're welcome. That's why the AP is shaped like this. So, but in the real world, you won't get this A directly. You have to figure it out yourself. And that's where things get interested. So, because in all systems, we know some things like this, but to get it to a form that we can use for good, in a system form, for a Kalman filter, for example. That how you come with this very simple idea to this form that you can use later in control engineering. That's what differentiates the students. Any other questions from the audience? Okay, that seems not to be the case. So I will close this session, and please work on the practicals and gather your questions. I would be really glad to help you with them if I could next week. And yeah, till next Friday, have a very nice weekend. Take care, and yeah, bye.
You too. Bye.
Bye.
Bye.